Imagine standing in a vast stone cathedral, the air thick and still around you, carrying the faint scent of aged wood and centuries of dust. Above you, a chandelier hangs from an invisible thread, suspended in the perfect silence before motion. You feel the coolness of the stone floor beneath your feet, sense the weight of the vaulted space pressing gently down. Then, almost imperceptibly, the chandelier begins to move, back and forth, a rhythm so smooth and hypnotic that your breath begins to synchronize with its journey through the air. There is no urgency in this motion, no struggle. It simply swings as if the air itself is cradling its weight, as if time itself has slowed to match this gentle, eternal pulse. You could stand here for hours and this rhythm would never change. You could return tomorrow or a year from now, and the chandelier would still swing with this same unhurried grace. There is something deeply restful in this constancy, something that speaks to a part of your mind that recognizes order, that finds comfort in predictability. In the year 1581, in the Cathedral of Pisa, a young student named Galileo Galilei sat in the pews one evening and observed the very scene you have just imagined. A chandelier, recently lit for the evening services, swung gently above the stone floor. The light danced across the vaulted ceiling, creating moving shadows that shifted and swayed. What made Galileo different from the countless others who had witnessed this sight was not that he watched the chandelier more carefully, but that he truly felt its rhythm. He listened to it. He began to ask questions that others had not thought to ask. As the light swayed back and forth, he wondered, does the swing take the same amount of time whether the chandelier swings in a wide arc or a narrow one? Does distance traveled matter? Or does each complete swing, regardless of how far the light travels, always take the same duration? He used the only timepiece available to him in that sacred moment, the steady beating of his own heart. He held his wrist up to the swaying light and counted the oscillations, the gentle arcs traveled by the chandelier, matching them against the rhythm of his pulse. 1 heartbeat per swing, 2 heartbeats per swing, back and forth. What he discovered was remarkable. Whether the chandelier swung in a wide arc or had begun to settle into a narrower, more gentle motion, the time required to complete each full swing remained essentially constant. The chandelier did not speed up as it swung through the wider portions of its path, nor did it slow as it approached the limits of its motion. There was a regularity, a predictability, a mathematical perfection that seemed almost impossible to explain. It was as if the chandelier possessed an internal clock, a rhythm that belonged to the system itself, rather than to the force that had set it in motion. This simple observation in a cathedral would eventually transform human civilization, though Galileo himself would not live to see the full implications unfold. He would later design a device called the pulsologium, based on this principle, to help physicians measure their patients' heartbeats with greater accuracy. But more importantly, he had glimpsed a fundamental truth about oscillating systems, that they possess an internal regularity, a rhythm that emerges naturally from their physical structure. In this way, Galileo opened a door to understanding the deepest patterns of nature, patterns that would echo through centuries of scientific discovery. To understand why a pendulum behaves with such remarkable consistency, imagine yourself standing still and then gently pushing against a wall. The wall pushes back against your hand with equal force, returning your hand to its starting position. Gravity works similarly on a swinging weight, but rather than meeting resistance from a solid surface, the weight experiences an invisible guidance, a gentle pulling back toward rest. Picture a weight attached to a string or a thin rod suspended from a fixed point. This weight is called a bob. When you lift the bob to one side, you displace it from its lowest point, its place of rest. But the moment you release it, gravity begins to act, pulling downward with a constant, unrelenting force. This force, measured at the Earth's surface, is strong enough to accelerate every object downward at the same rate, 9.81 meters per second squared. It matters not whether you drop a feather or a stone. Both accelerate at this same rate. But here is where the magic happens. As the bob begins to swing down, gravity pulls it back toward the center point. The bob swings through the lowest point of its arc with maximum speed, moving as fast as it will ever move during its journey. Yet at this very instant, something extraordinary occurs. The restoring force, gravity's pull, is at its minimum. The bob has momentum now. It overshoots, continues upward on the opposite side, begins to slow, and finally comes to a brief moment of stillness at the top of its arc before the pull of gravity becomes dominant again, reversing its direction. This cycle repeats again and again in a pattern so mathematically elegant that it seems almost carved into the fabric of reality itself. The motion is called harmonic oscillation, and it appears throughout nature at every scale, in the vibration of molecules within crystal lattices, in the rhythmic pulsing of distant stars, in the waves of sound traveling through the air around you. The period of a pendulum, the time required to complete one full oscillation, swinging out in one direction, returning to center, swinging out in the opposite direction, and returning once more to the starting position, depends primarily on two things. The first is the length of the string or rod from which the bob hangs. The second is gravity itself, that omnipresent force that holds you to the earth and keeps the stars in their courses. Here is the remarkable part, the insight that astonished physicists for centuries. The period does not depend on the mass of the bob. It does not depend on whether you swing it in a wide arc or a narrow one, at least not significantly for small to moderate oscillations. If you were to hold two objects of very different weights, say, a feather and a lead ball, and suspend them both from strings of equal length, they would swing back and forth with nearly identical periods. A feather and a lead weight would complete their oscillations in the same amount of time. This counterintuitive fact seems to violate our everyday intuition, yet it flows naturally from the mathematics of harmonic motion. Within the behavior of oscillation lies a beauty so profound that it transcends the realm of mere mechanics and enters the realm of poetry. The period of a simple pendulum, that amount of time required to complete one full swing, rests on a simple but elegant relationship with length and gravity. To make this tangible, imagine yourself holding a piece of string exactly 1 meter in length. 1 meter is approximately the distance from your fingertips to your shoulder when your arm is extended. Attach a small weight to the end of this string. Hold the string at your fingertips and let the weight hang freely. Now, gently pull the weight to one side and release it. Count slowly, 1, 2. By the time you finish saying 2, something precise will have occurred. The weight will have swung outward, returned to the center, swung to the opposite side, and begun its return. This cycle, this complete oscillation, takes almost exactly 2 seconds. 2 seconds, always 2 seconds, assuming Earth's gravity remains constant at your location. You could repeat this experiment 100 times, 1,000 times, and the duration would remain the same. The relationship between the length of the string and the time of the oscillation is absolute. A 1 meter pendulum will always take 2 seconds, approximately, to complete its cycle. This number, this perfect interval, depends only on how long the string is and the strength of gravity's pull. Nothing else matters, not the weight of the bob, not how hard you pushed it, not the air around it or the humidity or the time of day. Only length and gravity matter. This insight reveals something extraordinary about the universe. Simple physical properties generate predictable mathematical results. The cosmos follows rules. Medieval monks, centuries before Galileo, understood this principle even without fully grasping its mathematics. They sometimes used water clocks and mechanical devices based on similar principles to mark the hours of prayer throughout the day. The rhythm was reliable. The pattern held. They could depend on it. If you imagine two pendulums side by side, one short, about the length of your hand, and one long, about the length of your entire arm, you would observe something striking. The short pendulum would swing back and forth rapidly, perhaps completing 3 or 4 cycles in the time it takes your heartbeat to rise and fall once. The long pendulum would swing more slowly, more deliberately, completing perhaps only 1 cycle in the same duration. Yet each would be obeying the same mathematical law. Each would be as regular and predictable as the other. A massive iron ball and a small glass sphere, suspended from identical length strings, would oscillate with identical periods. This happens because while gravity pulls more strongly on the massive object, it weighs more after all. That massive object also possesses more inertia, more resistance to acceleration. These two effects perfectly balance each other, resulting in identical periods. In this way, nature achieves a kind of cosmic balance, a symmetry that speaks to the underlying unity of physical law. Mass and gravity dance together, and in their dance, they create equality. As centuries passed following Galileo's initial observation, the implications of pendulum regularity began to dawn upon the minds of mechanical engineers and inventors throughout Europe. The question became irresistible. If a pendulum's period could be known with such precision, and if that period could be made to regulate the mechanical components of a clock, then perhaps human beings could finally possess something they had long desired but never achieved: accurate, consistent timekeeping. Before the pendulum clock, all timekeeping devices were unreliable. Water clocks would lose accuracy as water evaporated or as the mechanisms wore. Mechanical clocks with weights would speed up and slow down unpredictably. Candles could not mark time consistently because burning speed varied with air currents and the quality of the wax. A traveler could not trust a clock. A merchant could not synchronize activities across distant cities. Civilization had no reliable way to measure the passage of hours. But a clock requires more than merely a swinging pendulum. A clock must convert that oscillation into regular ticking sounds and the precise movement of hands across a dial face. The solution was the escapement mechanism, a device of remarkable ingenuity that allowed a precisely measured portion of energy to be released with each swing of the pendulum. As the pendulum swung, it would trigger the escapement, which would permit a gear to advance by exactly 1 tooth before locking again, waiting for the next swing to release it once more. In this way, the pendulum's perfect regularity was translated into the regularity of mechanical gears turning at a predictable pace. Christian Huygens, a Dutch mathematician and astronomer, designed the first practical pendulum clock around 1656, building upon Galileo's observations with mechanical ingenuity and careful craftsmanship. Huygens' clock, combined with improvements by other craftsmen across Europe, finally achieved something that mechanical timekeeping had never achieved before: an accuracy of within minutes per day, when previous devices might lose or gain an entire hour over a day's time. For the first time, human beings could measure time with a precision that reflected the mathematical order underlying the cosmos. You can imagine the profound impact of this invention. Ships at sea, for the first time, could accurately determine their longitude by comparing local time with the time at their home port, a calculation that required precise timekeeping. Astronomers could now record observations with timestamps precise enough to track celestial objects and predict their positions with accuracy. Merchants and traders could synchronize their activities across distant regions, creating the foundation for modern commerce and international coordination. The humble pendulum, observed in a cathedral centuries earlier, had become the mechanical heart of the modern world. Beyond timekeeping, the pendulum revealed itself to be something even more profound. A tool for measuring gravity itself, that most fundamental force that holds galaxies together and keeps your feet upon the ground. The relationship between length, period, and gravitational acceleration could be inverted and rearranged, allowing physicists to determine the strength of gravity at any location on Earth. The Earth itself is not a perfectly uniform sphere, though from space it appears to be. Regions of denser rock lie hidden beneath certain areas, ancient mountains worn down over millions of years, compressed into the Earth's crust. Lighter material, less dense stone, predominates elsewhere. Vast quantities of iron and nickel concentrate in different regions. This hidden variation in Earth's composition means that gravity itself is not constant everywhere. Near the equator, gravity measures approximately 9.78 meters per second squared. As you travel toward the poles, gravity gradually increases. At the poles, gravity reaches approximately 9.83 meters per second squared. This difference seems tiny, less than 1%, but it is real. It is measurable. Why does this occur? The Earth is not a perfect sphere. The equator bulges slightly, and the surface at the poles is closer to the planet's center of mass. Gravity weakens with distance. Therefore, gravity is stronger at the poles. Imagine two identical pendulum clocks. One hangs in a study in London, ticking away the hours. Another hangs in a laboratory in Rio de Janeiro at the equator, ticking with identical precision. Yet over weeks and months, they diverge. The London clock runs slightly faster. Why? The invisible force beneath London is stronger. Gravity, so constant you never notice it, actually varies across the Earth. The stronger gravity at higher latitudes pulls the pendulum bob downward with greater force, causing it to swing with a slightly faster period. The clocks maintain their individual regularity, each one swinging at its own precise rate, but the rates differ because the gravitational fields differ. By measuring this difference, by noting exactly how many oscillations occurred in a fixed period of time, by comparing the actual period observed with the theoretical period, physicists could determine the local gravitational acceleration to remarkable precision. In essence, the pendulum became an instrument for mapping Earth's gravity, for understanding the hidden architecture of the planet beneath our feet. The invisible became visible through the simple back-and-forth motion of a suspended weight. This principle extended the reach of human understanding. As explorers traveled to remote regions, to the mountains of Peru, to the islands of the Pacific, to the Arctic tundras, they carried pendulums with them, just as modern scientists carry instruments and measuring devices. These pendulums revealed that gravity was not constant everywhere. The Earth possessed a subtle complexity in its gravitational field, reflecting variations in density and composition at great depth. The pendulum, so simple that a child could observe its motion and comprehend its rhythm, had become a tool of profound scientific investigation. As we step back from the Earth and allow our perspective to shift, zooming both outward and inward simultaneously, something remarkable becomes visible. The pendulum principle, this elegant relationship between regularity and oscillation, is not unique to clocks or cathedrals. It echoes everywhere in nature, appearing at scales both infinitesimally small and cosmically vast. On playgrounds across the world, children swing in simple pendulums constructed from rope and metal, experiencing the same harmonic motion that Galileo observed in a chandelier, using the beating of their own hearts to measure time in their minds. A child learns, without instruction, that pushing harder at the start does not make the swing go faster. The period remains the same. A child learns the rhythm of the swing, learns to anticipate the moment when the swing will return, learns to work with the pendulum's natural frequency rather than against it. Within atoms and molecules, a different kind of motion occurs. Electrons orbit nuclei in patterns determined by quantum mechanics, and these electrons oscillate between different energy states. When an electron absorbs light energy, it jumps to a higher energy state. When it falls back down, it releases that energy as light of a specific color. These oscillations occur at frequencies billions of times faster than a playground swing, measured in terahertz, in frequencies of thousands of billions of cycles per second. Yet the underlying mathematics remains identical. An atom behaves like a pendulum at the quantum scale, subject to the same harmonic principles that govern macroscopic objects. The colors of sunset, the appearance of the sky itself, the hues of flowers and of the sea emerge from these atomic oscillations, from electrons dancing in their own imperceptibly tiny arcs. At the other extreme, across the cosmic distances between stars, binary star systems perform a dance that echoes the same mathematical principles. Two massive stars, locked together by gravity, orbit their common center of mass in a cyclical pattern that might take years or decades to complete one full cycle. From our perspective on Earth, these stars appear to move together, oscillating back and forth in light and in the electromagnetic radiation they emit. The period of their oscillation depends on their masses and the distance separating them, exactly as the period of a pendulum depends on its length and the local gravitational field. Massive stars, separated by distances that would take light years to traverse, follow the same mathematical laws that governed a chandelier in a cathedral. Throughout the built environment, oscillation appears constantly. Bridges sway in wind patterns that match the natural oscillation frequencies of their structures. Aircraft wings flutter in harmonic modes during flight, vibrating at frequencies that engineers must account for during design. The surfaces of drums vibrate in patterns of nodes and antinodes, creating the rich timbres of music. The Earth itself oscillates after earthquakes, ringing like a bell that has been struck, with frequencies so low that the oscillations take hours to complete their cycles. Scientists can measure these oscillations using sensitive instruments, watching as the entire planet rings with energy released deep beneath the surface. Throughout the universe, from the subatomic realm to the cosmic scale, oscillation appears as a fundamental aspect of how matter and energy behave when they are displaced from equilibrium and allowed to seek their way back toward rest. As the centuries progressed after Huygens' initial success with the pendulum clock, master clockmakers in London, Paris, and Geneva created devices of extraordinary complexity and beauty. These clocks were not mere timekeeping instruments but works of art, combining mechanical precision with artistic design. Yet their makers faced a persistent challenge. The pendulum rod itself would expand and contract with heating and cooling. Metals behave in predictable ways as temperature changes. Brass expands more than steel when heated. The period of a pendulum depends on its length. Therefore, a pendulum rod made of a single material would lengthen in summer warmth, causing its period to increase and the clock to run slowly. In winter cold, the rod would shorten, causing the period to decrease and the clock to run fast. For a pendulum clock to maintain accuracy across seasons, this thermal drift had to be eliminated. Craftsmen developed ingenious mechanical solutions to this problem. The gridiron pendulum, invented by John Harrison around 1726, used rods of different metals, brass and steel, arranged in a specific pattern so that their opposing expansions and contractions canceled each other out. When the brass rods expanded in heat, the steel rods would contract slightly in terms of their thermal contribution, maintaining the overall length. Later designs incorporated mercury, that heavy liquid metal, in sealed vessels. As the temperature rose, the mercury would expand, and this expansion was carefully designed to precisely compensate for the expansion of the pendulum rod itself, maintaining constant period despite seasonal variations. These mechanical solutions represented not merely technical achievements, but profound philosophical statements. Human beings could craft instruments precise enough to reveal nature's subtle variations and precise enough to counteract them. By the 19th century, pendulum clocks had achieved accuracy to within seconds per year, a precision that would have seemed miraculous to medieval timekeepers who could not even measure time more precisely than the length of a shadow. The Greenwich Mean Time, established at the Royal Observatory in London, depended upon a series of pendulum clocks that defined the standard against which all world timekeeping was referenced. For nearly 2 centuries, the rhythmic swing of pendulums in darkened observatories determined the time across the entire planet. Ships set their chronometers by pendulum-based standards. Railway systems synchronized their schedules. International telegraphic communication depended on precise time synchronization. The coordination of global commerce and communication rested ultimately on the gentle back-and-forth motion of suspended weights in carefully controlled environments. Yet even at this height of precision, the limitations of pendulum timekeeping gradually became apparent as the 19th century gave way to the 20th. Pendulums, no matter how carefully constructed or compensated, remained susceptible to environmental factors. Vibrations from traffic and construction, changes in atmospheric pressure, the slow wearing of pivot points that allowed the rod to swing. Moreover, there were fundamental limits imposed by quantum mechanics and thermodynamics itself, limits that prevented pendulum clocks from achieving accuracy beyond a certain threshold without extraordinary measures and specialized conditions. The 20th century brought new technologies that would eventually surpass the pendulum's timekeeping capabilities while remaining fundamentally grounded in the same basic principles of harmonic oscillation. Quartz crystals, when subjected to an electrical voltage, vibrate at frequencies determined by their internal structure and chemical composition, approximately 32,768 cycles per second in typical wristwatches. Like a pendulum, a quartz crystal oscillates at a frequency that depends only on its intrinsic properties, not on the amplitude of oscillation or the strength of the electrical signal driving it. This made quartz an excellent foundation for precise timekeeping. Atomic clocks represented an even more refined expression of the principles Galileo first glimpsed in the Cathedral. Rather than a physical pendulum of wood or metal, atomic clocks employ the oscillations of atoms themselves, specifically, the transition of electrons between different energy states within the atom. A cesium-133 atom oscillates at a frequency of exactly 9,192,630,1770 Hz. That is, nearly 10 billion times per second. This frequency is so constant and reproducible that it became the official definition of the second in 1967. Modern atomic clocks maintain accuracy to within 1 second per 100 million years, a precision that transcends the bounds of human comprehension. If an atomic clock had been running since the birth of the universe, billions of years ago, it would have lost or gained, at most, mere seconds. Yet despite these advances, the fundamental principles underlying all these technologies remain unchanged from Galileo's initial observation in the cathedral. All oscillating systems, whether a chandelier hanging on a rope, a pendulum rod of polished metal, a crystal of quartz subjected to electrical current, or an atom of cesium excited by precise electromagnetic radiation, possess natural frequencies determined by their physical properties. When allowed to oscillate freely, they return to these frequencies with remarkable consistency and remarkable regularity. The restoring force ensures that displacement from equilibrium triggers a compensating motion that carries the system back toward its starting point. For a pendulum, gravity provides the restoring force. For quartz, it is elastic deformation within the crystal structure. For an atom, It is the quantum forces that govern electron behavior. In this way, precision timekeeping through the centuries represents not a departure from Galileo's initial insight, but rather an evolution of it, a refinement and extension. Each generation of timekeepers, from medieval water clock operators to modern atomic physicists, has sought to identify and exploit the most stable oscillating system available to them. The fundamental principle remains constant. Find a system that oscillates naturally at a particular frequency, measure that frequency accurately, and use it to mark the passage of time. The specific mechanism may change. The scale may shift from millimeters to nanometers to subatomic distances, but the underlying truth persists. There exists throughout the cosmos a fundamental tendency toward oscillation, toward regular, repeating cycles. This tendency appears so consistently, and at such varied scales that it seems to reflect something deeply true about the structure of reality itself. When physicists describe the behavior of waves, whether sound waves traveling through air, light waves traveling through vast distances of space, or quantum waves describing the probability of finding a particle at a particular location, they invariably use the same mathematical framework that describes the motion of a simple pendulum. Consider a guitar string hanging in the air, suspended at both ends. When you pluck it, the string oscillates at a fundamental frequency determined by three things: its length, the tension applied to it, and the material from which it is made. A shorter string oscillates faster. A tighter string oscillates faster. A denser material oscillates slower. A 1-meter string made of steel, tuned to precise tension, might oscillate at 440 cycles per second. The note A4 that orchestras use as a tuning reference. The string does not know which frequency to choose. It does not calculate or decide. Rather, given the physical parameters of its existence, it simply oscillates at the frequency dictated by the mathematics of wave motion. The beautiful, pure tone that emerges from a musical instrument arises from physical principles identical to those that govern pendulum motion. Light itself can be understood as an oscillation of electric and magnetic fields perpendicular to the direction of propagation. The frequency of this oscillation determines the color of the light. Violet light oscillates at approximately 750 terahertz, near the upper limit of human vision. Red light oscillates at approximately 430 terahertz, near the lower limit. In between lie all the colors of the visible spectrum, each corresponding to a specific oscillation frequency. Below red light, oscillations continue at frequencies humans cannot see with their eyes: infrared radiation, microwave radiation, radio waves. Above violet, oscillations continue: ultraviolet, X-rays, gamma rays. The oscillation occurs not in space itself, but in abstract fields that permeate the cosmos. Yet the mathematics remains the same. An oscillation at a certain frequency appears to our eyes as red light. An oscillation at a different frequency appears as blue light. An oscillation at a still different frequency is radio waves, invisible but perfectly real, carrying voices and music and data across continents and through space. In this way, the humble pendulum serves as a gateway to understanding phenomena spanning from the subatomic to the cosmic. Every oscillating system in the universe obeys the same mathematical principles that govern a chandelier swinging in a cathedral. The universe itself, according to the most modern theories of physics, might ultimately consist of vibrating strings and fields, engaged in a cosmic oscillation that generates all the particles and forces we observe. To contemplate a pendulum, really to sit with its motion and observe it deeply, is to contemplate a profound paradox. The pendulum is constantly in motion, yet it is perfectly regular and predictable. It traverses a range of positions, yet it always returns to the same point. It experiences forces constantly pulling it in opposite directions, yet it settles into a steady rhythm that does not degrade or change, that does not tire or lose its way. There is, within the eternal motion of a pendulum, a kind of stillness, the stillness of a system at rest with itself, in equilibrium with the forces acting upon it. A pendulum at its lowest point moves with maximum speed, yet at this very instant, the acceleration is maximum as the restoring force exerts its greatest influence, beginning to slow the bob's motion. Conversely, at the extreme points of the swing, the bob is momentarily at rest, yet at these instants the acceleration is maximum, pulling the bob back toward the center. Maximum velocity and maximum acceleration never occur at the same moment. They are always separated from each other in time, displaced from each other in their occurrence. This relationship, too, is universal. In all harmonic oscillation, displacement and velocity and acceleration maintain specific phase relationships determined by the mathematics of the system. Physicists speak of the amplitude of an oscillation, the maximum displacement from the equilibrium position, and the phase, which describes where in the cycle of motion the system currently resides. An oscillation can be described completely by specifying its amplitude, its frequency, and its phase. Two oscillations with identical frequencies but different phases will appear to be out of step with each other, reaching their peaks and troughs at different times. If two oscillations have the same amplitude and frequency but opposite phases, if one swings outward when the other swings inward, they will cancel each other exactly, their peaks and troughs negating one another. This cancellation phenomenon, called destructive interference, occurs in waves throughout nature and has been harnessed by humans to suppress noise and unwanted vibrations. To observe a pendulum is to observe a fundamental truth about existence, that systems can be displaced from equilibrium, can be set in motion, and will then establish patterns of behavior determined by their inherent physical properties. A pendulum does not require constant attention or constant input of energy to maintain its motion. Once set in motion, it will continue oscillating at its natural frequency until friction and air resistance gradually dissipate its energy over time. The pendulum teaches us that regularity and predictability can emerge naturally from the laws of physics, without requiring external control or guidance. This lesson extends far beyond clocks and bridges to encompass how we understand the natural world and our place within it. We have journeyed together through the elegant world of oscillation, traveling from the cathedral in Pisa where Galileo first perceived the underlying mathematics of motion, across centuries of technological advancement, to the atomic clocks that now define the very fabric of time itself. We have seen how a simple mechanism, a weight suspended from a fixed point, reveals principles that echo throughout nature, from the smallest atoms to the largest cosmic structures. The regularity of a pendulum speaks to something profound about the universe, that beneath apparent complexity and variation lies order, that systems displaced from equilibrium naturally seek to return, and that this return journey follows predictable mathematical laws. For centuries, this regularity allowed human beings to measure time with ever-increasing precision, transforming civilization in the process. Ships found their way across oceans. Telescopes mapped the stars. Communications networks synchronized themselves across continents. All of this rested ultimately on the discovery that a simple mechanical oscillation could be counted and used as a standard for duration. Yet the deeper wisdom of the pendulum transcends its practical applications in timekeeping. To contemplate an oscillation is to contemplate the nature of stability and change. A pendulum is stable. It returns always to its lowest point when left to itself. Yet it is also dynamic. It does not hang in frozen stillness but moves constantly. This balance between stability and motion, between order and activity, mirrors the character of life itself. We, too, oscillate between states of activity and rest, between growth and reflection, between reaching outward and returning to our center. The pendulum teaches us, in its silent way, about the deep patterns underlying reality. It shows us that simplicity can contain great complexity, that mathematical elegance can explain physical phenomena, and that the universe operates according to laws that are knowable and understandable to those patient enough to observe carefully. The pendulum's swing, repeated countless times across the centuries, from cathedral chandeliers to atomic transitions, reminds us that regularity and order are fundamental features of existence. Allow yourself now to drift, as if you are drifting with the pendulum itself. Imagine yourself in that cathedral, or perhaps in a dimly lit room where a simple pendulum hangs before you. Feel how your breath begins to match its rhythm, in as it swings one way, out as it swings the other. Feel the gentle pull of equilibrium, the way the pendulum always returns to its rest point, always finds its way home. There is no struggle in this motion, no resistance. There is only the eternal return, the gentle rhythm that has continued for centuries and will continue long after you have fallen asleep. Allow your own thoughts to slow, to settle, to return like the pendulum to their resting place. Let go of the day's urgencies and complications. Feel yourself becoming like the pendulum, returning always to your center, finding rest not in immobility but in the gentle motion of your own natural rhythm. The oscillations continue, regular and eternal, holding all things in their embrace. You are part of this rhythm. Your heartbeat is an oscillation. Your breathing is an oscillation. The very neurons in your brain fire in patterns of rhythm and rest. In this darkness, in this quietness, allow yourself to settle into the pendulum's eternal pattern. Back and forth, always returning, always finding the way home. Final word count, 5,731 words.